so let's have a look some more at this biaxial stuff. So what we did here, we did this example yesterday in class. And the point with this that I would make is in red there, that you can start with, when you do your design type calcs, you're going to know the stresses in the X and Y directions. We have ways of figuring that out depending on what it is you're designing. Once you have those, though, there can be stresses at different angles inside the object you're designing that are greater than the X and Y stresses. So you have to watch that, because when you design something, you generally design it for the largest stress. So we want to figure out how to find the largest stress that occurs in an object that we're going to design. All right. Now, if we go back to this sketch here that we were looking at, we do see uniaxial, which is a simpler form of biaxial. It's a special case. And what we had there was some relationships that will hold for biaxial, so I think they're worth mentioning. They're kind of simpler to see in uniaxial, I think. So what we had here in uniaxial is that the fact that the maximum normal stress occurs on a plane that is 90 degrees away from the plane of minimum normal stress. So the maximum and minimum planes are 90 degrees apart. There's the plane for maximum, there's the plane for minimum, okay? And they're 90 degrees apart. The shear is 0 on both of those planes. And then we have a plane midway between the two where the maximum shear is, okay? And that kind of makes sense to me, that the maximum shear, the slipping, would be midway between the maximum polar push and the minimum polar push, okay? So halfway between those two at 45 degrees, you've got the tau max plane. Also on that plane, you have the average normal stress. So that's the relationship in uniaxial, and those hold for biaxial too, okay? So let's figure out what the maximum stress might be. It's called a principal stress is the term for this, because this is what a designer wants to know. So what we would do to find it is first we start with our basic normal stress equation right there. And that's on your formula sheet. I can't remember which equation. It's on the left about midway down. As I've mentioned a couple of times now, it's really common to use this equation, and I suggest having some way of just automatically calculating it. It's equation 25. So what you can do with this is you can first realize kind of what's happening there. The knowns are sigma x, sigma y, and tau xy. Those are the things that you already know. When you know those, you can calculate the stress at an angle, which we call sigma x1. That's the variable. So, as you learn from calculus, if you want to maximize something, what you do is you take a derivative and set that equal to 0. So what we're interested in first is finding the angle at which this maximum stress occurs. So we take the derivative of all of this expression with respect to the angle. So we're going to go d sigma x1 d theta and set that equal to 0. So what we're then going to do then is take the derivative on d theta there of all these terms on the right. Okay, because we're setting the d sigma d theta to 0. With everything else here, these are just constants here, so they go to 0 when we take a derivative. Here we're going to have sigma x minus sigma y over 2 times the derivative of cosine 2 theta. So the derivative of cosine 2 theta is negative sine. And then we have that, is that chain rule? You got to pull that constant out. I can't remember what you call that. Yeah, chain rule. Okay, so you pull that out. So that's minus 2 sigma x minus sigma y over 2 times sine 2 theta. And then the same sort of thing again. We're going to take the derivative of sine 2 theta, get cosine 2 theta, but we have to take the 2 and pull that out front. So we get plus 2 tau xy cosine 2 theta. All right, and that's all equal to 0, the sum of those two things. So we can take this term, take it to the other side of the equation. It becomes positive then, divide the 2's out, and we get sigma x minus sigma y over 2 sine 2 theta is equal to tau xy cosine 2 theta. So we can divide both sides by the cosine, divide both sides by sigma x minus sigma y over 2, and we get tangent of 2 theta is tau xy sigma x minus sigma y over 2. Okay. So that's the formula that we're going to use. It's still a little bit involved, of course, but what that does is that tells us where the maximum stress occurs, where the maximum normal stress occurs. And that's equation 27 is what that is. So this is pretty key here because it tells us where that maximum stress is going to be in an element. Okay. Now, if we want to know what the maximum normal stress is, we have to take that expression and solve it for theta. So theta would be 1/2 arctan. So we do it inverse tangent of both sides and get 2 theta is arctan tau xy, sigma x minus sigma y over 2. And then that's 2 theta, so we have to divide both sides by 2. So what we get there for the actual angle is it's 1/2 arctan tau xy divided by sigma x minus sigma y over 2. Okay? So that's where the maximum stresses act. Remember that arctan has 2 solutions, so there's going to be 2 angles that fit that equation, all right? So that those angles are going to correspond to the maximum normal stress and the minimum normal stress. Okay, there's 2 solutions, one max, one min. If we take that angle and plug it into this expression, I'm not going to go through all the algebra on it, but it boils down to this equation right here. Okay? So sigma 1 and 2, the principal normal stresses, the max and min normal stresses are equal to sigma x plus sigma y over 2 plus or minus sigma x minus sigma y over 2 quantity squared plus tau xy squared. That's what that boils down to. And that's equation 28. Okay. So if you know what sigma x, sigma y, and tau xy are, which generally speaking we do, you can figure out what the maximum and minimum normal stresses are in the object you're designing by using that equation right there. Okay? You can also figure out what angle it acts at by using this equation right here. Okay? So that's good information there. That's equation 27 right there. Okay. Okay. Now, if you take that arctan angle here and plug it into the shear equation, that'll boil down to 0. Okay. And I don't want to spend time going through the algebra, but if you take that angle for the maximum and minimum normal stresses, plug it into the shear equation, the shear comes out to 0, which means that shear is 0 on the sigma 1 and 2 planes. Sigma 1 and 2 are the maximum and minimum stresses. Okay? So we got 2 planes. Okay? They are 90 degrees apart because what we have here is this tangent 2 theta formula is going to have 2 solutions. Okay, if you remember that tangent is delta y over delta x, let's just say we've got one angle here that's 3 to 2. Well, this other angle here would be minus 3 to minus 2 if I just extend this line back. So those are the 2 angles that would be expressed by a given tangent, let's say. So this angle and that angle. Those 2 angles would have the same tangent, and they're 180 degrees apart. Those are tangent 2 theta, so if you take half of the 180 degrees, you get the 2 angles themselves are 90 degrees apart. Okay? So what's going on here is we got a minimum normal stress, a maximum normal stress, 90 degrees apart in the element, and the shear on those planes is 0. That's basically what we got here so far. So we good? So, and the uniaxial, again, is a special case. What you see there is we got maximum and minimum, and they're 90 degrees apart, and the shear is 0 on those planes. So that's a special case of what we're talking about. Okay. All right, now we can do the same thing again to find tau max. We can take the maximum, or the general shear formula, take the derivative with respect to theta, set it equal to 0, and sort it out. And what we're going to get is this equation for the angle at which the in-plane maximum shear stress acts. Okay? So tangent of 2 theta will be negative sigma x minus sigma y over 2 divided by tau xy. Okay. Now, if you notice, that's the negative reciprocal of the tangent formula for normal stress. Now, negative reciprocals, if you start looking at how those of tangents there, so negative reciprocals are 90 degrees apart. So if that's 4 to 2, this line here would be negative 2 to 4. Okay, they're negative reciprocals. If that's the case, they're 90 degrees apart. So the 2 theta angles are 90 degrees apart. That means the actual theta angles are half of that, 45 degrees apart. Okay? So when we do this, take the derivative of the shear with respect to the angle, set it to 0, we find the maximum and minimum shears in an element. They are 45 degrees off of, or the maximum shear, in-plane shear is 45 degrees off of the planes for the maximum and minimum normal stresses. Okay. And again, uniaxial, the plane for maximum shear is 45 degrees off of the plane for the maximum normal stress. Okay, they're 45 degrees off. That's what we just found out. If we take that angle and plug it into the shear formula, we get something else here. We're going to get the maximum in-plane shear formula, tau max in plane. Okay. And that is 1/29. If you take that angle, this angle right here, the angle of maximum or tau max in plane, and plug it into the general normal stress formula, you'll find that the normal stress on that plane is sigma x minus sigma y over 2, which is the average normal stress. Okay. So what we're doing here, we're going through this biaxial stuff, and we're finding out a lot of information about what happens in a biaxially loaded element to find the maximum and minimum normal stresses and the maximum shear and where they act. And this is basically equations 27, 28, 29, and basically we'll stick with that for now. So equation 27 is the angle at which the maximum and minimum normal stresses act, given by this tangent 2 theta formula. Right there. 28 occurs when you plug that angle into the general normal stress formula. You get this formula here with a radical in it, plus or minus, because there's a max and a min, so there's 2 solutions there. And then 29 is the maximum in-plane shear stress, which acts 45 degrees off of the planes of maximum normal stress. So when you're designing something, you look at this stuff because this will tell you what the max and min stresses are that you need to design for. Now there's a couple little pieces to this, but we'll come back and get them as we need, okay? Because I know this is a lot of information to kind of digest all at once. So let's start by just looking at a basic example of this, and let's figure out where these principal stresses are and the angles at which they act, okay, and what their magnitudes are. So why don't we start with that? Okay, so we're on page 357. Let's have a look. So let's say we've done the numbers here and we know the x and y stresses are as shown. Let's figure out what the principal stresses are, which are the max and min in-plane stresses. And let's find out what the maximum in-plane shear stress is, okay, on that element. So for starters, just write down sigma x, sigma y, and tau xy. What are those? And get the proper numbers with the proper signs in there. So negative 52, 90, positive for, so negative 52 for sigma x, positive 90 for sigma y, and then what's the sign on tau xy? It's negative, okay? We all good with that? Because by convention, because they set up the equations that way, you go with that shear. That shear would rotate the thing clockwise, and that's negative, so that gets a negative, okay? Now, in the past when we did this, we found an angle too, but or we just pulled the angle off the sketch, but this time we're not, because we're going to find the maximums. We got to calculate where that angle's at, okay? And to do that, we just plug into that formula and find where that angle's at. So we want to solve for tangent 2 theta is tau xy divided by sigma x minus sigma y over 2. Okay, so you just go ahead and plug that stuff in. Okay. So we got negative 40 over negative 52 minus 90 over 2. Take a tangent of that, you get 0.5634. Now, once I have that, I know there's two angles. So I calculate the 2 theta angle, because that's the angle that I'm going to plug into the formula. So I want that. I take half of it and get where the first angle is. I know the other angle is 90 degrees off of that, so I add or subtract 90 to it and get the second angle, and then I double it because I know I'm going to plug that into the formula again to get the second stress. So that's kind of how I work that. And solve for 2 theta, I take half of it and get theta, that's theta 1, add 90 to get theta 2, and double it if I need it, because I'll run it a second time. Okay. So that's how I work that. And then I just have to start plugging it in, okay? Now that's the angle at which the maximum normal stress acts, maximum or minimum, I should say. It's one or the other. And so what I can do is plug that angle into the general formula. So the way I do this stuff is I use the general normal stress formula. I plug in that special angle where I know the maximum acts, and I plug it in, and I use formula 25. Plug it into that. Okay. And when I run those numbers, I'll get negative 62.5. So what I know is at an angle of 14.7 degrees, I've got a negative 62.5 megapascals, and that's the maximum or minimum stress that acts in that plate. Now, I don't like using, now sometimes I will if it's going to help me, but generally speaking, I don't use that equation 28. The reason is when I use equation 28, which has that plus or minus the radical, I don't know what angle it acts at. It just gives me a number for maximum and minimum stress. It actually gives me two numbers because there's a plus or minus radical in it. I prefer to do it this way because then I know which stress acts at which angle. Okay? So I just plugged in 14.7 degrees, and actually, of course, I'm plugging in twice that because the formula calls for 2 theta, and now I know that the minimum max stress in that element is negative 62.5, and that acts at 14.7 degrees.
So we can calculate it twice, once for each angle, whichever one's bigger.
Yeah, now that's a little, yeah, essentially, yes, you're right. There's a couple little twists on that, but yeah, that's the idea. Just run it both 2 times and find the 2 stresses, and then start looking at it. Because I want to know where they act. I just don't want to know what they are. Usually I want to know where they act. So this tells me right where they act, okay? Okay, are we good with that? Now we can do it a second time, plug in the second angle, and I'll get positive 100.5 megapascals. Okay, that's the other one. So what I have now are the max and min normal stresses in the element, and I know what angles they act at. So I can go ahead and fill in that sketch there with the max and min normal stresses. So now I have a good visual representation of what's happening there. So once you get those stresses on there in their proper orientation, which one goes where? I have that element drawn up. We could label that little angle there. You should be able to figure out which of the two that is. It's just a small angle there from the vertical plane going counterclockwise. So let's start with the angle. What's that angle down there? Yeah, 14.7. So where are these stresses going to go on that sketch? So at 14.7, what do we got going on there? 62.5 negative? Something like that. We all right with that? It's pushing in from that angle. So normal to that 14.7 degree plane, we have that stress, and then 90 degrees off of it. We got it going the other way, and that's 100.5. And then what's the shear on those planes? Because those are principal planes with maximum and minimum normal stress. You remember that? What's the shear on the maximum normal stresses planes? It's 0, yeah. So there's no shear on those planes, okay? Just pure push and pull, pure tension and compression, okay? So, we good with that? So what this means, to me anyway, is if this thing is going to fail, which normally speaking things don't, you know, but failure is a good way to visualize things. If this thing's going to fail in tension, I would expect it to fail on that tensile plane. I would expect it to pull apart like that. So I would expect there to be kind of a edge like so, and that side to pull up a bit and over, and then that edge, you know, a matching edge over here, and this other side pulling down. That's what I would expect. So if there was a tensile failure. If there was a compressive failure, I would expect these sides to kind of crush in, kind of thinking like an accordion, you know, kind of like that. And it would kind of crush in. This will be tough for me to draw, but it would turn into more of a rectangle. And I could kind of think like if this were aluminum foil, you'd kind of have fold lines kind of going like that, and coming in like that. Okay? So that's the meaning of this. So what I have there is actually I call it a tensile failure and a compressive failure. Now, failure doesn't normally happen, so I don't mean to infer that that these things will always break at these, you know, on account of these stresses, but it's a good way to visualize what's going on. Okay? So, we doing all right with that? All right, now we do have this shortcut equation, and let's kind of have a look at where that comes from, because there is a kind of a relationship in these equations that leads to all sorts of shortcuts. So we good with this? So I'll go backwards a little bit here. See, if you look at these formulas, which honestly I'm not using, but all the same, you know, they exist. We have these formulas that will automatically get you the maximum, the principal stresses, which are the max and min normal stresses, and the maximum in-plane shear stress, okay? So there's equation 28. That's the principal normal stress equation. Sigma x plus sigma y over 2, plus or minus that radical there. See, the plus or minus means there's a min and a max, okay? That's the meaning of the plus or minus. And then the shear equation is the same radical, okay? So that can be used to generate shortcut equations, because it just so happens that the shear, the equation for maximum in-plane shear is that radical, okay? So what you can do is substitute the shear in for the radical on that equation. All right. So instead of saying sigma x plus sigma y over 2 plus or minus the radical for the maximum in plane shear principal stresses, okay, sigma 1 and 2, you can say it's sigma x plus sigma y over 2 plus or minus tau max. Okay, you can go ahead and just substitute tau max in for that radical. That's what you can do. And I'm on page 340 is where I am. Okay. So if you do that, you can get a couple other kind of shortcut equations that are kind of handy. Okay, the first one is if you add sigma 1 and sigma 2, what you got is sigma x plus sigma y over 2 plus tau max, or the radical, whichever one you want to use. And then the other one then, if you add sigma 2 to it, you're going to get sigma x plus sigma y over 2 minus either the radical or tau max, whichever one you want to use. Well, you got a plus and a minus. Those just go away. So what you get there is sigma 1 plus sigma 2 is sigma x plus sigma y. Because you're adding sigma x plus sigma y over 2 to sigma x plus sigma y over 2. That just equals sigma x plus sigma y. Okay? So there's that little shortcut equation we use. Now, the other thing you can do is subtract. So if you take sigma 1 minus sigma 2, you get sigma x plus sigma y over 2 plus tau max minus sigma x plus sigma y over 2 minus tau max. Well, now this time the sigma x plus sigma y over 2 stuff cancels. You get sigma 1 minus sigma 2 is 2 tau max. So a quick formula for tau max is plus or minus sigma max minus sigma min over 2. Okay? So those are just some shortcut formulas. And they're on your formula sheet too. You've got equation 30 and equation 31. So those are little shortcuts that you can use sometimes if you want to find something in a hurry, okay? So what this one here means is instead of doing that, running that equation a second time, we can just use this equation right here. If you know sigma 1 or 2, and you know, of course, you know sigma x and y, you can find the other. So if you know sigma 1, you can find sigma 2 using that equation, okay? So that's a quick way to get one principal stress when you already have the other. That's equation 31. All right. So we're good with that? Now the vocabulary gets a little involved too. Okay, so we're good with that so far? Okay. Now, there's a lot of ways to describe this. Sometimes they're called principal stresses, sometimes the max and min principal stresses. Okay, now here are the two principal stresses that we came up with. Now this is actually negative. So I think from a mathematical point of view, the maximum is 100.5 and the minimum is negative 62.5. But from an engineering point of view, I don't really use those terms. What I would say is the maximum tensile stress is 100.5, the maximum compressive stress is 62.5. That's how I would look at it. Okay? So the words max and min are actually kind of more mathematical definitions. Engineering definitions might be different. You know, because you could conceivably have sigma 1 is, 50 megapascals, and then sigma 2 is negative 70 megapascals.
Is that much tensile stress at that angle? So at another angle, it might not necessarily fail.
Yeah, right. Yeah, that is the angle at which the tensile stress maxes. Every angle has its own different tensile stress or different stress on it. This is the one that is the biggest, and we figured out where it is and how big it is. Right. Okay. All right. Now, if we had an element where we got these answers, and someone asked me what's the largest stress, I'd tell them it's 70 compression. Okay. A mathematician might say it's 50 because that's the most positive value, but as an engineer, I'd say the biggest stress is 70 compression. That's numerically the largest. The absolute value is the biggest. Okay. So it's just a matter of how you word it. Okay. Yeah, right. That's how I look at it, because that's the what's most likely to cause me problems. Okay. So just be aware of that. The thing is, and also what I call sigma 1, you might call sigma 2. It doesn't really matter. All I care is what's the principal stresses and what angles do they act at. You can call them sigma 1 or sigma 2 or really whatever you want, but what matters is what those stresses are and where they act. Okay? Because that can come up when you're looking at an answer key. You might get sigma 1 and you go, well, the key says that's sigma 2. What's the deal? It doesn't matter. As long as you got the proper stress at the proper angle, the 1 and 2 designations are kind of arbitrary. Okay? All right. Okay, so there's the sketch there that we came up with. Now we can also come up with shear, maximum in-plane shear too. Okay. And so what you do to find that is you take your one of your angles. We're using theta 1. That first angle we found 14.7. Add 45 to it. That's where the maximum shear stress acts. So the maximum shear is always 45 degrees off of the principal planes, always. Okay, so if I double that angle, because that's what the formula calls for, is twice the angle, I'll get 119.4. Then I can plug it into my general shear stress formula. And when I do that, I get positive 81.5, and that occurs at 59.7 degrees. I don't like using those radical formulas generally because I can't draw a sketch off of them very well. If I find the angles, plug them into the general formulas. By the general formulas, I mean formulas 25 and 6. I know exactly the stress and what angle it acts at, and I can draw it up, which is what I'll want to do. Okay. All right, now what I can do then, I know that at 59.7 degrees, I've got a shear stress of 81.5. I can find the average normal stress, that's the stress that acts on the maximum shear planes, negative 52 plus 90 over 2, it's 19. So now I can make a sketch that shows me about the maximum shear in plane. Okay. So the maximum shear planes have the average normal stress acting on them. What I found, see, and this is why I like to do it this way, at 59.7, when I run the general shear formula, I get positive. Okay, so what that means is this shear stress on the 59.7 degree plane rotates the element counterclockwise. So it goes on like that. And once I've got one, I know the rest, because the other one will meet in that corner, and then the other two will meet in the opposite corner. So once I have this one on the 59.7 degree plane, I can figure out which way all the others are pointing. Okay. So that's what that shear sketch will look like. I've got an average normal stress of positive 19 on all 4 planes. I've got that initial shear on the 59.7 degree angle going that way, and everything follows from that. Okay. Now I can also find a maximum shear using this other formula, plus or minus sigma 1 minus sigma 2 over 2, which is plus or minus sigma max minus sigma min over 2. So I can go ahead and plug in my maximum normal stresses and minimum normal stresses, take the difference, divide by 2, and I'll get 81.5. So that's another way to do it. But again, that's a plus or minus. You're not quite sure how to draw up the sketch when you do it that way. So I prefer to use the general formulas with the proper angle input. We doing all right with that? Okay. So by running these formulas, and generally they're angular formulas, so you just run one, the tangent 2 theta formula that I give you on equation 27. If you run that, you'll find the angle at which these things act, okay? And then you just use the general formulas to figure out what the stresses are. This equation is 25 and 6. So just by doing the one tangent 2 theta formula, you can find where that one of the principal stresses act. And once you've got that, you can figure out where all the other ones act. And you can plug those angles into equations 25 and 6 and figure out what the stresses are in plane. So we all right with that? Okay. All right, now lots of information here, and it's just one of those things, I'll throw a lot of information at you, you just have to kind of work with it to kind of learn it. It might take a few days and some practice at this to get all this stuff figured out. But let's look at another little aspect of this, one more little extra thing here to be thinking about, and that's on 360. Okay. And that has to do with that formula that we just developed right there. And that's formula 30. Okay. Now, if you're staying in plane, sigma max and min are sigma 1 and 2. Easy enough, just plug those in, and you can find tau max in plane, at least at plus or minus. So you're finding its absolute value, basically. However, one thing we have to remember is that biaxial stress is applied in 2 directions. However, we're dealing with 3-dimensional objects. Okay? So we have to be thinking about that a little bit too, because there is a third stress, sigma z, which when we're doing biaxial loading is 0. Okay? But it exists, and we need to remember that. Okay, now there's a couple different things that can happen here. See, there's an element, I've pulled out the principal element out of this thing. So there's a plate that's being loaded in the x and y directions. There's a zoom in on that principal element showing the principal stresses that I found. 50 tensile at that angle there, going to the right, 10 compression, and then I showed sigma z on there at 0, okay? Now, if you really want to thoroughly investigate and find what the absolute maximum shear is, you would take 50 minus a negative 10 and divide it by 2. That's sigma x minus sigma min over 2. And that's a plus or minus 30 because there's a plus or minus in that formula, okay? But you should also consider this plane up here. That thing might shear across at 45. And what's happening with that, and I don't quite have the right one. It's the one up top, really, that I want. It would be this one here. This would be a better one to draw. Sorry about that. So we have that angled plane on the top that looks something like that. And we're going to pull on that, as you can see, with 50. Now the z stress goes that way, and it's 0 because sigma z is always 0. We should investigate that plane too, because even though it's only biaxial loading, they're 3-dimensional objects. So I might get a shear going at 45 across that plane because the shear acts 45 degrees off of the principal angles. And to do that, I would investigate sigma max, which is 50, minus sigma min, which is 0 in this case, over 2. And that comes out to be plus or minus 25, because there's a plus or minus formula on the formula. So what I call tau max absolute, which is my design stress on this, is the bigger of the two. It's 30. It's the in-plane stress. Okay? So that's one example where we're checking what I call that out-of-plane shear stress, because it might govern, and we want to watch for that, okay, when we're designing something. Now the case below, this will be a little bit more significant. If I have 50 and instead of a negative 10 for the other principal stress, I've got positive 10, tau max in plane becomes plus or minus 50 minus 10 over 2, which is plus or minus 20. But the out of plane shear stress, again, on that edge up there, I've got 50 pulling that way, and I've got 0 in the Z. So that's, I don't know how to draw that, I guess. No, it's not that way. It's more like that. So that's 0, and that's 50. I have to consider this case also. And sure enough, this one will be 25. 50 minus 0 over 2, plus or minus 25. That one governs that time. Okay? So you got to be a little careful of this and always check that possibility that the out of plane shear stress governs. And the formula for that is sigma max minus 0 over 2. It's just sigma max over 2 is what it comes out to be. In some cases it governs, in some it doesn't. But I've seen cases where the out of plane shear stress is twice what the in plane maximum shear stress is. So it is something you got to be aware of, because that could get you a very unwelcome surprise if that were to happen, all right? If you had failure on account of that. There is kind of a general rule on this, and the general rule is if the in-plane principal stresses have different signs, you'll get minus a negative when you run that, and the in-plane tau max will govern. If the in-plane maximum, the principal normal stresses have the same sign, then the 0 here will get you the bigger of the two. The out-of-plane stress will govern, okay? So if the principal stresses have different signs, the in-plane shear stress governs. If the principal stresses have the same sign, the out-of-plane shear stress will govern, okay? Good with that? Talking there, I know, but that's kind of the last little bit of this. So it's something you got to keep an eye on. Okay. And later on, a couple of weeks, we'll see an example where that out of plane shear stress governs, and it's a big deal. Okay. All right. So on 362, I've got another example that illustrates this. So I just have, I think, worked out biaxial principal stress example. We got that element there, so what? We got 120 for sigma x, 50 for sigma y. We got this shear stress is your reference shear stress. That's going to rotate the element counterclockwise, so that's positive. Plug all that into the tangent 2 theta formula, solve for the angles. 2 theta is 40.6, half of that's 20.3. Add 90, you get 110.3, and double it, you get 220.6. Okay. Plug that first angle into the general normal stress formula. You get one of the principal stresses, it's 131.1. Plug the second 2 theta into the formula, you get the other normal stress, 38.9. Alternatively, you could use that shortcut equation. So now we got the principal stresses, 131.1 positive and 38.9 positive. So there's a sketch that shows what those look like. Now notice in this case, the words maximum and minimum do have meaning, don't they? Because that's the maximum stress, that's the minimum, okay? So it's hard to just have one way of expressing that. It kind of depends on the signs on those things, how you describe them. All right, so now we know if we're going to design this thing, we're designing it for 131.1 megapascals. Now, if we want to know what shear to design for, we can find tau max in plane. We find the angle for tau max first. 20.3 plus 45 is 65.3. Double that for the angle to put in the formula, it's 130.6. Run the numbers, and you get the maximum in-plane shear stress, negative 46.1 at the 65.3 degree angle. Why don't you get that on that sketch real quick, see if you can get that drawn up. And then the average normal stress is 85. Let's take a minute and see if you can do that, and then we'll carry on and get the rest of this. Okay, so what's going on there? You check out the angle, it's 65.3. You check out the shear stress, it's a negative. So put the negative 46.1 at the proper angle, and then everything comes off of that. Okay. So something like that. Good with that? Okay. So I've got the maximum shear stress, and then I've got the average normal stress on there. Okay. Now, let's figure out what the design shear is for this thing. We got the design normal stress, it's 131.1. That's what we're going to design this for. Now let's figure out what the design shear stress will be, and that's tau max. So we got to consider two of them, one in plane, one out of plane. The formula is tau max is equal to plus or minus sigma max minus sigma min over 2. So if I'm going to go in plane, I take the maximum in plane normal stress, which is 131.1, subtract off the minimum, which is 38.9. So I'm taking away a positive 38.9. So it's negative 38.9 over 2. And that's the plus or minus 46.1. That's what I got earlier. But if I look at the out of plane tau max, oops, I'll come back here. There we go. It'd be 131.1 minus 0 because sigma z is 0, okay? And what that's going to do is get you a larger shear stress than the in plane. So if you're going to design this thing for shear, that's the number right there, okay? And that's why you got to be careful about this stuff. See, that's not quite half, again, as much as the 46.1, okay? It's quite a bit larger. So you have to be aware of that. So if you know that shear occurs on that red line that I'll mark here, right there. It's right on that line at 45, running across that that plane. Okay. So that's a little bit on that. What do we got? We got Friday. Just trying to think. We should have stuff to do. What are we going to do? That's. So I'm going to assign 201 and 202. How about getting them in on? Let's see. Just trying to think when we should do this one. Well, let's make them do Wednesday for now. We'll try that and see if that works. So do Wednesday. What's that now? 201 and 2. So that'll be 131, and that'll be 201 and 202. So 201 and 2 are due Wednesday the 30th. No, it's not the 31st. It's the 29th, right? So do the 29th, 201 and 2. We okay with that?